Dear students, under the topic Integer Linear Programming, we are going to learn the branch and bound method. The integer linear programming can be solved by two methods, that is, the cutting plane algorithm, and the next method is branch and bound method. Now, here in the question, we are asked to use branch and bound method to solve the following linear programming problem. The question is to maximize z equal to 5x1 plus 4x2 subject to the constraints x1 plus x2 lesser than or equal to 5, 10x1 plus 6x2 lesser than or equal to 45, with the restriction that x1 and x2 are non-negative integers. The difference between an LPP and ILPP, that is the linear programming problem, and the integer programming problem is that the solution space of integer linear programming problem should be integers, whereas in linear programming problem we used to, if we get the decimals also, the solution space is accepted, whereas in integer linear programming problem the solution space should not have decimal values, they should be only integers. So the method that we are going to adopt to solve this problem is the graphical method. So as we solve the LPP, we are going to draw the graph for this given problem. The two axes of the graph will be x1 and x2. Now, first step is we have to write these inequalities as equality constraints and mark them as equation 1 and equation 2. So these inequalities we have written as equalities and we have marked them as equation 1 and equation 2. Now, in order to find where the first constraint touches the x2 axis, we have to put x1 as 0. And in order to find the first constraint touching the x1 axis, we have to put x2 as 0. So let us put x1 as 0 first and see what is the value of x2, and then we have to put x2 as 0 and find the value of x1. By doing so, we obtain the points 0, 5 which touches the x2 axis and 5, 0 which touches the x1 axis. In a similar way, we should do the same for the second constraint also. So let us do that. So now here by putting x1 equal to 0 in the second constraint, we find at which point the constraint touches, that is the constraint touches the x2 axis. And here by putting x2 equal to 0, we can find at which point the constraint touches the x1 axis, that is 4.5, 0, and this is 0.75. And so after finding all these 4 points, now we have to find the point of intersection between the two constraints, that is the two equation. So in order to find the point of intersection of 1 and 2, we have to solve 1 and 2. So in order to solve it, we can multiply equation 1 by 10. So after multiplying, we get 10x1 plus 10x2 equal to 50. Then equation 2 I have taken and written, and then we are on solving these two equations, this will get cancelled, and here we have 10 minus 6, so it is 4x2, and 50 minus 45, which is 5. So the value of x2 will be 5 by 4, which is 1.25. And so on substituting the value of x2 in the first constraint, what we will get, here we will substitute x2 equal to 1.25. So the value of x1 will be 5 minus 1.25, and so the value of x1 we have obtained to be 3.75. So this will give us the point of intersection of the two constraints. Now after finding all these points, we can draw the graph. So I have drawn the x1 axis. So this is x1 axis, and here we have the x2 axis. So now we shall draw the first constraint. Now if you see, the first constraint touches the x2 axis at 0, 5 and x1 axis at 5, 0. So 0, 5 is here. So this point is 0, 5, and here we have 5, 0. So let us join these 2 points. We will get the first line. So this gives us the first constraint, and if you see, the first constraint is bounded, that is lesser than or equal to. So the region below this, so here we have lesser than or equal to, and so the region will be the region below the line. Now we will draw the second constraint. If you see, the second constraint is touches the that is x2 axis at 0 comma 7.5. So 7.5 is over here. So at this point it touches the x2 axis, so 0 comma 7.5, and it touches the x1 axis at 4.5 comma 0. So here 4.5 we have here, so this is 4.5 comma 0. So let us join this point and this point now. Yes, we have joined. Now if you see, this constraint is also lesser than or equal to constraint, and so the region below this has to be shaded. So what is the common region for these two constraints? So if you see, the region below this line takes up all this, and for this line takes up this region, and so the common region will be bounded by these points, that is, this is the point of intersection. So here, so I will just draw the boundary of the common region. So this is the common region. We can name the end points. This is point O, this is A, this is B, and this point is can be taken as C. So the region O, A, B, C is the common region for both the constraints. So let us shade them. So this is the common region bounded by the points O, A, B, C. Now we have to find the value of maximum Z, that is Z, at these points. So let us see which value is maximum. So I have taken and written the solution space here, that is O 0 comma 0, and then A is this point 0 comma 5, B is the point of intersection which is 3.75 comma 1.25, which we have found previously, the point of intersection. So this point, and then we have the point C which is 4.5 comma 0. So at these points let us find the value of Z and let us see which gives us the maximum. So at the point O it is 0 comma 0, so x takes the value 0, x1 takes the value 0, and x2 also takes the value 0, which gives Z to be equal to 0. And then at the point A, 0 comma 5, so x1 is 0, so this term becomes 0, and here 5 4 times is 20, so the value of Z is equal to 20. And here at these points, when we substitute 3.75 multiplied with 5 plus 1.25 multiplied with 4 gives us Z to be equal to 23.75. You can substitute and check it. Similarly, when we substitute x1 as 4.5 and x2 as 0, so 4.5 multiplied with 5 gives us Z to be equal to 22.5. And so if we see, the maximum is for Z equal to 23.75 at the point 3.75 comma 1.25. But if you see, the solution space is not an integer, they are in decimal. Since we are solving integer linear programming problem, the solution space should be integers, that is x1 and x2 should be integers, whereas here we have decimal values. And so we have to proceed this problem further by using branch and bound method until we get the solution space as integers. So now let us take and write the solution that we have obtained, which is Z is equal to 23.75 for x1 to be equal to 3.75 and x2 is equal to 1.25. So this is the first solution space, which are integers. Now we have to divide this problem, that is we have to find subproblem for this. How are we going to do that? Now out of these two integer values, which is the largest one? It is 3.75, and this 3.75 lies between 3 and 4. So somewhere we will be having 3.75 in between these two. So the idea of the problem is we are going to eliminate this region by choosing the value of x1, that is x1 we will choose the values before the integral value, that is x1, to be lesser than or equal to the lowest integral value, which is 3, and x1 to be greater than or equal to the highest integral value, which is 4. So we are eliminating this in between portion in the graph. So when we do so, we will get two problems with two constraints added to it. That is, the original problem added with the constraint x1 lesser than or equal to 3 will give us the subproblem 1. So this will give us the subproblem 1. And the original problem added with one more constraint x1 greater than or equal to 4 will give us subproblem 2. So I will write and show that to you. So if you see here, this is the original problem given to us. Now in this problem, we are going to subdivide this as two problems, subproblem 1 and subproblem 2, by adding these two constraints. That is, when this problem is added with the first constraint x1 lesser than or equal to 3, we get subproblem 1. When this constraint is added to this problem, we get subproblem 2. And how did we get these values? By eliminating the in-between values. That is, we found the x1 and x2 values. Out of that, we chose the maximum, and we found the integral values with the lowest integral value and the highest integral value of this 3.75. And eliminating this portion, we chose values lesser than or equal to 3 and took it as one constraint, and we chose values greater than or equal to 4 and we have taken it as another constraint. And so we have obtained the subproblem 1 and the subproblem 2. You can see that here. This gives us the subproblem 1, where the one more constraint x1 lesser than or equal to 3 is added to it. And here we have the subproblem 2, where x1 greater than or equal to 4 is added to it. So now we will draw the graphs for these two subproblems, and we will find out whether the solution space has become integers or not. If they are integers, we will conclude the problem, or if not, again we have to branch and find the bounds for that problem. So first we will do for subproblem 1, we will draw the graph. So here we have the subproblem 1. We know that the first constraint, the values are, we previously saw the line is like this. We have already done this. So the same. For the second constraint, the line will be this one, 7.5 and 4.5. This also previously we have seen, and this is the point of intersection. Now one more constraint has been added to this. What is that? x1 lesser than or equal to 3. And already this is lesser than or equal to constraint. This is also lesser than or equal to constraint, the first two. And the next one is this. So x1 lesser than or equal to 3. Where is x1 equal to 3? It is at this point. x1 equal to 3 is at this point. So lesser than or equal to 3 we have to take. First of all, we will draw the line x1 equal to 3. So this will give us the line x1 equal to 3, and we have to choose the region lesser than or equal to this, which means the region will be bounded by these 4 points. So now this region has been eliminated from this. We can see that this region has been eliminated. So these are the 4 points. So let me shade the region and show you. And if you see that this is the new region where this point is 0, 0, and this point is 0, 5, and this point is at x1 equal to 3. So it will be 3, 0. And this point is the point of intersection of the first constraint and the new constraint that we have obtained. So let us find that. So for the subproblem 1, the first constraint is x1 plus x2. We will write it in equality is equal to 5. And the new constraint is x1. Again we will write in equality, which is equal to 3. So now we have to substitute this x1 equal to 3 in this equation. So what we will get? So from this, if you put 3, x2 will be equal to 5 minus 3. And so the point of intersection will be x2 is equal to 2 over here. So the point of intersection is 3, 2. So therefore the point D I have given here, which is 3, 2. And so we have O, A, D and E. Now at these points we have to find the value of z and we have to see which gives us the maximum. So now here we have the solution space for subproblem 1. At 0 comma 0, z is equal to 0. Previously we have seen this. At 0 comma 5, so if you put x1 as 0 and x2 as 5, we get z to be equal to 20. And then at 3 comma 2, that is the point D, the value of z will be, now if you put x1 as 3, 5 3 times is 15. And then x2 as 2, so 4 2 times is 8. So 15 plus 8, which is 23. And then we have 3 comma 0, so if you put x1 as 3, 5 3 times is 15 and x2 is 0, so z is equals to 15. Now if you see, the maximum value of z is 23. So now in a similar manner we have to check for subproblem 2 also. So let us do that. So if you see, for subproblem 2, the constraint that is added to the problem is x1 greater than or equal to 4. So let us draw this graph now. You can either draw a separate graph or in the same graph also you can do. This is subproblem 1. Now we are going to do subproblem 2. I am going to do in the same graph itself. You can either do it in that way or you can have a separate graph also. It's not an issue. So this is now here we have subproblem 2. What is the constraint that is added? x1 greater than or equal to 4. So I have to draw the line x1 equal to 4 in this graph. So x1 equal to 4 is at this point, and so the graph will be like this. So what is the region over here? What is the region that is bounded? Here it is greater than or equal to, and these two lines are lesser than or equal to. So when we see the region below this line and below this line and greater than this line is this particular region. So this region is the required region. And here we have 3 points. Since it forms a triangle, we have 3 points. So let us mark them. So this point is 4 comma 0. So 4 comma 0. This point is 4.5 comma 0. So we have got 2 points. In fact, we can name them. I'm going to name this as P, Q and R. So the point P is 4 comma 0. R is 4.5 comma 0. The point Q is the intersection of this new constraint with the second constraint. That is the intersection between these two. So this constraint and this constraint we have to find, like how we did previously for subproblem 1. We have to do for these two constraints. We have to find the point of intersection. So first we will write them in equalities. So I have written those constraints into equalities. Now here x1 is equal to 4. So if we substitute 4, it is 40 plus 6x2 is equal to 45. So from this 6x2 will be equal to 45 minus 40, which is 5. And so the value of x2 will be equal to 5 by 6. So that gives us 0.83. So now therefore the value of x1 is 4 and x2 is 0.83, which gives us the point of intersection Q, that is this point. So that point is 4 comma, so this is 4 comma 0.83. Now at these 3 points we have to find the value of z and we should check which gives us the maximum. So let us do that. So here I have taken and written the 3 points. Now let us find the value of z. So at this point z is equals to, so x2 is 0, so 5 4s are 20. And at this point 4 comma 0.3, so 5 4 times is 20 and 4 multiplied with 0.3 and we have to add it. What we will get is z is equal to, we get 23.32 at this point. And then here x2 is 0, 5 multiplied with 4.5. So that gives us z to be equal to 22.5. So if we see which gives us the maximum, so this point. So this is the solution space of the subproblem 2. Now let us write it in the branch form. So if you see here we had the solution of the original problem given. So that is this solution I have taken and written here. and then we had two branches and two constraints added to the problem. One was the subproblem 1 and this was the subproblem 2. So the solution space for subproblem 1 is here, subproblem 2 is here. That is what we obtained here. So this solution space I have taken and I have shown here. So these two. Now if you see here, the solution are integers because the value of x1 is 3 and the value of x2 is 2. So this gives us integer values for x1 and x2. So we observe that the problem is optimum at this point. But the subproblem 2 has not given as integers because one value is integer, another value is a decimal value 0.83. So again this problem has to grow as a branch. So how to branch it now? Now if you see, here we have 4. So this is an integer value, so we need not worry about it. Whereas this value is the decimal 0.83. So now this value has to give rise for the branch. So how to do that? Now 0.83 lies between two integral values. So what are the two integral values? 0 and 1. So 0.83 lies between 0 and 1. So if you see, let me show you here. So 0.83 lies between 0 and 1. So somewhere here it will lie. So we have to eliminate this region now. So the values we have to take for, now we are branching for x2, right? So the values for x2 will be lesser than or equal to 0 and here x2 greater than or equal to 1. Then this portion will be eliminated. And so the two constraints, that is now the subproblem for already subproblem 3 we are having, subproblem 2 we are having, that we are branching. So we will get subproblem 3 and subproblem 4. So this constraint will be added to the original subproblem 2 and it will give rise to subproblem 3. And this constraint will be added to subproblem 2 and it will give rise to subproblem 4. So let us do that. So if you see here, first we had the original problem which gave rise to subproblem 1, subproblem 2. Now here we have subproblem 2. Now this gives rise to subproblem 3 and subproblem 4 which we have here. Now the constraint x2 lesser than or equal to 0 is added to this and it gives rise to subproblem 3, and the constraint x2 greater than or equal to 1 is added to added and it gives rise to subproblem 4. So these two values, as I told you, we have done. So subproblem 3 and subproblem 4 we have. Now let us draw the graphs for this and let us find the solution. I will show that to you in the graph that we already have. So now this is subproblem 3. So these two constraints we have already drawn, and x1 greater than or equal to 4 gives us this region. Now adding this constraint to it, x2 lesser than or equal to 0. Now first of all, what is x2 equal to 0? It is the axis x1. So this line is x2 is equal to 0. Now here the constraint is x2 lesser than or equal to 0. So the region below this line or straight at this line, because it is equality also we have lesser than or equal to. But if we choose the region below this line, it is out of the required region. It is not intersecting with this. So we have to choose this line, that is x2 equal to 0, since the constraint is lesser than or equal to 0. The lesser region we cannot choose since there is no intersection, whereas x2 equal to 0 is this line. So only a line intersects with the required region, and so the 2 points will be P and R alone. So this point we have to check the value of Z, and at this point we have to check the value of Z for subproblem 3. So we will have only 2 points in the solution space which are P and R. So let us see that. So as mentioned in the graph, for subproblem 3 we have only these 2 points, as we are concerned only about that straight line PR. So at the point P 4, 0 we have, and so what will be the value of Z? 20. And at the point 4.5, 0 the value of Z is equal to 22.5. So now which gives us the maximum? This value. In a similar manner, we shall check for subproblem 4. So subproblem 4 here we have, and the new constraint that is added is x2 is greater than or equal to 1. So the region will be here. So in this region, we are going to take, first we have to see what is x2 equal to 1. So here we have 1 for x2 equal to 1 is here, this line. So the line is over here, but it is out of the required region. So since, because it is greater than or equal to, so since this line is greater than or equal to, so beyond this line, not below this, it is beyond this line, the region. So when we see there is no intersection, so therefore we will be having no feasible solution, that is we will obtain an infeasible solution in this case. Therefore for subproblem 4, the solution at this stage is infeasible. So therefore for subproblem 3, this is the solution, and so the branch will be like this. So we had two constraints at this point. So here this was the original problem, this is subproblem 1 solution space, subproblem 2 solution space, and it was branched into two, where one constraint added was x2 lesser than or equal to 0 and another constraint was x2 greater than or equal to 1. And so this is subproblem 3 and this is subproblem 4. So if you see for subproblem 3, we have obtained this solution. x1 is 4.5 and x2 is 0 and the value of z is 22.5. So that I have written here. And here it is, it has infeasible solution, and so I have written no feasible solution. Now in this, now if you check this, again we do not have an integer value, it is a decimal value. So this has to branch again. So how the branch will be? Now here this is 0. Now the only value is x1 is equal to 4.5. So if you see for 4.5, it will lie in between the integral values 4 and 5. So we are branching for x1, right? So this is x1. So we have to choose x1 lesser than or equal to 4 and x1 greater than or equal to 5 in order to eliminate this region. And so these are the two new constraints added to the problem. And so the subproblem, here we have, this is subproblem 5 and this is 6. And so that constraint I have added here, x1 lesser than or equal to 4, and we have obtained subproblem 5. So this one. The next constraint, x1 greater than or equal to 5 I have added here, and we have obtained the subproblem 6. Now for this problem we have to draw the graphs. So let me show in the same graph. Now if you see, so for subproblem 5, if you see the graph, now here since it is greater than or equal to 4 we have here, and also x1 lesser than or equal to 4 we have. x2 lesser than or equal to 0 and x2 greater than or equal to 0 we have. So it will be one single point. So, and that point will be 4, 0, this point, since here we have x2 lesser than or equal to 0, which will be this line, and particularly at the point x1 lesser than or equal to 4 and also greater than or equal to 4, it will be only this point now. So therefore at that point we have to find the value of z. So here we have the solution space and the point is 4, 0, and so the value of z will be 20. And so this will give us the optimum solution at that point. Now we have to check for subproblem 6 that we have written here. The new constraint added is x1 greater than or equal to 5. And if you see, when we take x1 as a greater than or equal to 5, the region is beyond this and it is out of the intersection region. And so in this case the solution will be infeasible. And so therefore the solution space will be, this is the solution of subproblem 5, and for subproblem 6 it will be an infeasible solution, and so it will branch like this. So when we have taken x1 lesser than or equal to 4, this problem, that is x1 lesser than or equal to 4, we got this solution. And when we have taken x1 greater than or equal to 5, we have obtained no feasible solution. that is infeasible solution. So hence the problem is done. So the only lower bound that we could see, so this is a lower bound, and this is also because it didn't have integers, so this will give us the lower bound, and in fact this gives us the optimal solution. So this gives us the optimal solution. Hence, we have concluded the problem with the optimal solution to be z equal to 23 at the point x1 equal to 3 and x2 equal to 2, which are integer values. Hence, we have obtained the integer solution for x1 and x2. So this is the solution space, if you see. So I hope you would have understood this concept. Thank you.